Most of us walk through life assuming time is a rigid, universal metronome. A second here on Earth feels identical to a second on the moon, or anywhere else in the cosmos. Albert Einstein's theory of general relativity defines gravity as the physical warping of a four-dimensional fabric called spacetime. To see how extreme this warping gets, imagine you and a friend out in deep space. You stay safely aboard the ship, while your friend begins a direct freefall into a massive black hole. Because gravity bends time itself, the two of you will experience two different, mutually exclusive realities of the exact same event. These perspectives are both 100% physically real. The black hole literally fractures chronology, making your friend's rapid plunge and your view of their infinite freeze equally true. This diagram illustrates gravitational time dilation, the rule that stronger gravitational fields cause time to pass slower. The clock deep within the gravity well ticks at a fraction of the speed of the clock in flat space. From your ship, you watch your friend approach the event horizon, the absolute point of no return. As they reach the exact edge, you see their watch tick slower until it freezes entirely. To you, they come to a dead stop, stuck in time forever. You never actually see them fall inside. As the light struggles to escape the gravity well, they slowly fade to red sight at this glowing orange boundary. To the rest of the universe, your friend is a frozen ghost, trapped on the edge of the horizon for the rest of eternity. Your friend's experience is the opposite. Locally, their watch ticks at a normal pace of 1 second per second, a measurement known as proper time. They feel no physical barrier or pause at the event horizon. They cross the boundary smoothly in a finite, measurable amount of time. If they look back out at the universe they are leaving behind, they witness a bizarre consequence of their slowed time. Because their internal clock is moving so much slower than the rest of the cosmos, they intercept millions of years of incoming light signals in the final seconds of their descent. This causes the entire external history of the universe to appear in fast forward, with stars burning out and galaxies colliding in what feels like moments. While you watch your friend die in extreme slow motion, your friend watches the entire universe die in fast forward. Inside the event horizon, the standard rules of reality reach a breaking point. In normal space, we have 3 dimensions of flexible direction where we can choose to move, and 1 dimension of time that forces us forward. Inside a black hole, space and time mathematically swap roles. Space becomes the dimension of inevitable, forced downward motion toward the center, while time becomes the flexible coordinate. Escaping a black hole is impossible because space itself is now dragging you forward, just as time once did. Flying away from the center is as physically impossible as trying to travel backward to yesterday. This inversion redefines the singularity, the infinitely dense core of the black hole. The singularity functions as a literal moment in the astronaut's absolute future, rather than a physical location they can navigate around. At this specific moment in time, gravitational forces become infinite, and the curvature of spacetime becomes absolute. According to general relativity, time itself stops existing. Our current understanding of physics results in a divide by zero error at this point. The math we use to describe the universe fails to function at the singularity. Until we develop a unified theory of quantum gravity, the absolute center of a black hole remains the point where our understanding of time reaches its limit.